So, welcome to the 2024 mock exam, Examcraft, question C3. We've got the roof of a building with surfaces E, F, G, H, A, B, C, D. Okay. Now, the elevation plan of the roof surfaces are given. They're intersecting. Surfaces A, B, C, D have a pitch. A, B, C, D. A, B, C, D have a pitch of 50 degrees to the horizontal plane, and E, F, G, H have a pitch of 60 degrees to the horizontal plane. What does that mean? That means that, okay, surface A makes an angle of 60 degrees or 50 degrees to the horizontal plane. So you can see this here, surface E. So surface A makes an angle of 50 degrees to the horizontal plane. Surface B also makes an angle of 50 degrees to the horizontal plane. So I'll just do it there one more time. So if I can snap on to surface B, well, I might get surface C here. No angle is coming up, but surface C makes an angle of 50 degrees as well. Surface B makes an angle of 50 degrees to the horizontal plane, and so too the surface D. So that's what they mean by pitch. Okay. Then surfaces E, F, G, and H make an angle of 60 degrees to the horizontal plane. So they make an angle of 60 degrees to the horizontal plane. That's here, projecting as an edge. Now, part A, draw the plan of the roof surfaces. Part B, draw the elevation. The heights, some of the heights are missing in elevation, but the word pitches is going to help us figure it out for part B. Part C, draw the dihedral angle between surface A and B. And part D, find the true shape. Now, here's the solution. Don't worry too much, all the writing there. We're just going to focus on drawing the plan. Alright, angle 15 degrees, size of the square 120. Okay, and then the offset squares inside. So we're going to get cracking on that. So our XY line, now 15 degrees can be done with the two set squares, okay, together. Alright, it can be done with the protractor, so I have the two set squares to 45 and then 60-30 sitting on it, and I get 15 degrees. Or it can be done with the protractor or the adjustable set square. So I'm going to mark in then 120. Now, so we can join our diagonals together to get our center. Now the offset squares inside 10, 40, alright, 50, or sorry, and 10 and 10 is 60. So we're going to get our middle. I don't know why this is so shiny there. Just give me 1 second there to deal with. So we're going to get our center now. Now we're going to mark out 5. Okay, and then 20 from the 5. And we're going to mark another 10 from that. So we're out 5 from the center, 20 from the 5. Okay, and an additional 10. Now, then I'm going to draw them in. So the outside one, heavy there. The inside one, hidden detail. And then heavy again. And then I can carry these around parallel to the sides of the square. So I'm just going to pause and do that. Now, so we've gotten part A done, draw the plan. Now we have to do part B, draw the elevation. The problem is, we don't know this height. Okay, nor do we know this height. But we can solve this, right? So we have the complete outline of surface A in plan. And we have the angle it makes to the horizontal plane. So we can look along this line here in plan. So we're going to look along this line here at the base of it, because it's the true length. And when we because it's parallel to the XY line in plan. And when we look along that line, it's going to project as a point. And the key thing is the surface A will project as an edge. And if surface A projects as an edge, we can apply the angle of 50 degrees to pitch. And then we can carry our end of surface A in plan up to intersect that. Where that intersects there, we've got the height of surface A, because that's the edge view of the surface, that's the horizontal plane. So we can see the pitch of 50 degrees, and the end of it will calculate its height. And then surface E is done the same way. We bring up surface E, surface E is going to project as an edge view, because this line is going to project as a point, because that line is a true length when you look along it. You can apply in 60 degrees, and this height here can be applied there. So we'll quickly look at that in SolidWorks. So I'll go down, that's my auxiliary vertical plane. Here's my auxiliary elevation. So there's both surfaces projecting as edges. Okay. Then I carry on the tops of the points, or the ends of the surfaces rather. So look, see, I can carry them on to meet those angles, and then I get the heights calculated there. They calculate the height and elevation, and then I can draw in my elevation. So I'm going to look along, right, this line here in plan. And the reason it's this one is because it's the true length, because it's on the XY line elevation. So I've looked along that line there that you've seen. I'm going to carry on surface A. I'm going to carry on this line here. This is for surface E. And I'm going to carry on the top of surface E here. I'm going to draw in my x1, y1 line, which represents an edge view of the horizontal plane. I'm going to label these points now. 0, 1, 2, 3. Okay, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right. So we had said that the pitch of surface A was 50 degrees to the horizontal plane. And the x1, y1 line is an edge U of the horizontal plane. So there's the HP. So I'm going to get my protractor. And I'm going to mark the angle of 50 degrees here. And I'm going to continue there to the hidden detail line. So now we have the height of surface A right there, which we'll take in a moment. Now we'll do surface E now here, which will F, G and H will have the same height. So we have to go up, okay, an additional 25, 15 and 10. This is the start of surface E here. We're going to draw a line parallel to the x1, y1 line here. Now 10, okay, and 15. Now we're going to get our protractor here, and we're going to mark in, okay, an angle of 60 degrees. Because it says the pitch is 60. So we're going to mark in an angle of 60 degrees here. This is the height of E, F, G and H, and this is the height of A, B, C, D. Okay, so we can plot this into our elevation then, right? So we know we can project our lines up. So we have our 0 on our base, our 3, our 1, and our 2 on our base. Then our 8, we can project up our 8. And we're going to get our compass. As spoken about, we're going to take the height of this here from our auxiliary elevation. We now have our altitude for 8, 9, 10 and 11. So 8, 9, 10 and 11 we've got. So we can bring 8 up to that. 11. 10. Sorry, why am I saying 8, 9, 10, 11? Sorry, why was I saying that? 4, 5, 6, and 7. Sorry, my apologies. 4, 5, 6, 4, 5, 6, and 11. So 4, 5, 6, and 7. Now, so I'm going to join these points together. So 4 to 0, 7 to 3, 5 to 1, and 6 to 2. And then we have to climb in altitudes of 15 and 10. So you can see we're going to bring these points straight up from the altitude of 15, and then we're going to bring additional numbers up from plan. Now, so we're going to bring 8, 11, 10 and 9 up. 8, 11, 10 and 9. So here, point 8 is here. Eleven is here. Sorry, I'll write 8 there. 8 is up there. No, there. Then 9. And 10. Now, I'm going to heavy these in. Then we have to step up for our altitude. Okay, for the 12, 15, and 14. So this is the altitude of them there. 13/12. So I can get with my compass, put it on the X1, Y1 line. Take the altitude there, lift, mark it there, and that's the altitude of all the points. Now, so I have 12 there. I'm going to put the rest up, and I'm going to mark them in. So 12 to 8, 15 to 11. 13 to 9. And 10 to 14. Now, so we've then done, we now have to find the dihedral angles between surfaces A and B. We have to find the dihedral angle between surfaces A and B. Now, in the 3D, you can look immediately along the line of intersection and see the edges. But that's in 3D, okay, not in 2D. We'll have to do additional work. So in 3D, we can see the line of intersection as a point. So I'm seeing surface A there, surface B there as edges. So A, B, and the line of intersection is appearing as a point. The line there is in blue. The line there you can see appears as a point, and then you get the dihedral angle between them straight away. Okay, that you can see. This is the angle here. Unfortunately, in 2D we can't do that, right? We need the line of intersection to appear as a true length to look along and see as a point. Our line of intersection is not a true length plan because it's not parallel to the XY line elevation. So we're going to look perpendicular to that by doing an auxiliary elevation, and then we're going to project along that true length of the line of intersection. So there's the auxiliary elevation showing the true length, and there's a second auxiliary there getting the planes as edges and the line of intersection. Note that the second auxiliary isn't actually done on that plane in real life. Okay, that's only a clarity for explanation. So we're going to look perpendicular to the line of intersection, take an auxiliary, then look along it, and then to shorten, okay, the amount of work I have to do from the dihedral angle, I'm going to pick a point on the base, bring it back. So essentially what I'm doing is splitting surface A and surface B into two triangles. I'm just going to shorten that down rather than take all the points, which works out massive space on the sheet. Right, so we begin. So I have my x1, y1 line. Parallel to my line of intersection. My x1, y1 line. Now my projection lines. So surface B, surface A, and then I'm taking my line of intersection 5, 1. So 5 and 1. Now I'm going to get my height from elevation. So I need the height of 4, 4, 5 and 6. So the height of 4, 5 and 6 that I'm getting from my elevation. So I'm putting that there, there. Now, here's 1, here's 5, here's 4/6, okay, and then this is 0/2. Right, and as I said, I'm going to pick a point along the base here and bring it back, just to shorten these into two triangles. Call them M and N, just to shorten the space that I need. This is a true length because we're now looking perpendicular to it. So if I look along this, it's going to project as a point. There's surface A, surface B is behind it. G, E, F, G, H. So I'm now going to look along this line of intersection. I've looked along the line of intersection, and I'm going to pick the 2 points, M1, N1. I don't need to bring the rest of them over because it just gets very big, the amount of space I required. I'm going to draw in my X2, Y2 line. So we're going to take our distances from our X1, Y1 line back to plan for our second auxiliary here. Alright? So we're going for M. There. Okay. N. There. You can use a datum line now if you want. Okay, on the line of intersection. You can see again the line of intersection 1, 5 is going to project as a point. Right, so our dihedral angle is coming up here. And then it's always good practice to mark in your dihedral angle. There we have it there. Now another way I want to show you do the dihedral angle is using something called rebatment. Right? So in rebatment you can put a triangular plane that fits in underneath, snugly underneath the two surfaces. So I'm just turning A and B to transparent. So we've got a triangle here that fits neatly into the two planes. Okay, and the edge of the triangle, that line there, has to make a right angle to the line of intersection when it's a true length. Then we're going to rotate the plane down. So we're going to rotate that triangular plane down onto the horizontal plane. And the true shape of that plane is the dihedral angle. in plan view. The true shape of that plane is, or that triangular lamina, is the true shape of the dihedral angle in plan. So you can see that's the distance there. So how to do that is, look, you pick any point in the XY line, draw a line perpendicular to the line of intersection, bring it back, rotate this down, bring it back to the line of intersection, join the points. So I'll do that here a bit slower and a bit more zoomed up. So I pick any point on the XY line. Okay, as long as provided it's under the line of it'll be under the line of intersection. Draw a line perpendicular to the line of intersection. Project that point back at the same angle as you projected your auxiliary. Now, rotate. Well, I didn't need to bring that point back. You just need to rotate it down. You can bring this back here. And then the dihedral angle is right here. Our dihedral angle, 114 degrees for there, using our protractor. Now the last part, find the true shape of surface A. So we have to look perpendicular to that, right? Now, so I'm going to get my surface A, I'm going to rotate it down. That's what's happening in my auxiliary out there. Okay, I'm rotating the edge U surface A. Here's the path of the points on surface A being rotated in 3D. Here's surface A being rotated in 3D until it's onto the horizontal plane, and the true shape is there in plan view. So how that works is, in our auxiliary elevation, we're going to rotate the edge of the surface A until it's on the x1, y1 line. We're going to bring it back. These points are perpendicular to the hinge line there. Now I'd probably be tight on room on this now. It might just run off my page a little bit. So I'm going to get my compass. And I'm going to rotate the edge of the surface A. Until it's on the x1, y1 line. And going to bring points 5 and 4 down perpendicular to the hinge line, or parallel to the x1, y1 line. Now, here's the true shape of surface A here. And that's the question complete, because that surface is now on the horizontal plane in plan because it's on the x1, y1 line in our auxiliary elevation. Well, Okay, and our auxiliary elevation is the edge of the horizontal plane here. So that's 4, 5/4. 5/4. Okay, 4 comes to here, 5 comes to here. So this is the true shape. And that's the question done. So that was enjoyable. Thank you.